Hello guys, I am Doc. Today we will discuss about support vector classifier. Before we get into it, I would like to discuss something about the classifier. The classifier is something which help us distinguish between the two classes. For example, if I have a spam and a ham, there would be a classifier. Classifier can be something like a line or a plane or a two-dimensional plane which will help me distinguish between the spam and a ham. Similarly, the classifier could be something which help me distinguish between the two images of the cat and a dog. In the last lecture, we discussed about revising maximum margin classifiers. So today we would be revising some concept of it, as it would be very important in discussing the support vector classifier. So maximum margin classifier, as you can see in sorry for that. In maximum margin classifier, as you can see that there is a line. So as you can see, there is a line which is acting as a classifier. The line which is basically classifier is something, I would say, it's a formula which is available, some mathematical formula which is available, and by putting the values of each of the point in that formula, we calculate that that it belong to that this belong to class A or it belong to class B. So as you can see, I have 2 points, the green points and the red points. The red points are labeled as negative sample labels and the positive sample labels. So green points are the positive sample labels. So this is the so by using the classifier and by making the classifier equal to 0, as we discussed in the last lecture, we came to the concept of the hyperplane, and we created a hyperplane, and we said that the hyperplane is something which divides the two classes, and anything behind the hyperplane is belongs to class A, or we can say in this case the positive sample labels, and anything falling in the forward direction of the hyperplane can be labeled as a negative sample labels, or a class B entity. So this is simple. This is a simple concept of maximum margin classifier. The maximum margin classifier is named because we maintain a margin between the nearest point of the two classes. In this case, this is the nearest point between with this hyperplane, and this is the nearest point with this hyperplane. So we maintain some margin m between the two classes, and this classifier or this hyperplane is a very strict hyperplane, and it says that no green or the positive sample labels can appear on the other side of the hyperplane, and similarly no negative or the red sample can appear on the other side of the hyperplane. So this was the formula which we derived this is basically the label. When we multiply label with the distance, or I could say that the label, this is the weight array, and this is the y array. uh, if you are still confused in the formula, I would ask you to go and view my last video about maximum margin classifier. So we derive this formula. If each point satisfy this formula, means if the label of that point, for example, the label is positive here +1 and label is negative here -1, if each point label into the w array is nothing but w naught plus it is nothing but a coefficient array, w1 plus w2, it's a nothing but a coefficient array, I would say, and y is nothing but a independent variable or the regressors array. So y would be something like this, 1 plus x1, this is the characteristic array, plus x2, and so on. So we said that the dot product of w and y into its label will be always greater than m. If this condition is satisfied, then this hyperplane is good enough for separating these two classes. This is a maximum margin classifier. So the basically maximum margin classifier, we maintain a margin between the there is some margin between the nearest point of the two classes. So there is some problem with the maximum margin classifier, because this, I think this is the ideal situation which we have. There are two the red in the real life scenario, the red point can be on the other side of the some red points can be on the other side of the class, and similarly the positive label can lie on the negative side of the class, means there is no strict boundary between the two. But this hyperplane suggests that this hyperplane suggests and can only exist if there is some strict boundary between the two. But this is very rare in the real life situation. The real life situation, it appears like this, that majority of the positive negative labels on one side and majority of the positive label on the other side, and there is some boundary which is separating them. There is some boundary which is separating them, but there is intermixing, there is an intermixing of the two classes. So there are, I would say, it may be the noise, or it may be some real life situations where this class may fall, the characteristics of this class may match some of the characteristics of the other class, but that is only in the rare situation. So this is the practical situation, and in this practical situation the maximum margin hyperplane cannot exist, or the maximum margin classifier cannot exist. So the problem of this classifier is that it is very strict classifier. So we need some classifier which allows us to somewhat intermix between the two classes. So we need some classifier which allow us some misclassifications. So we came to the concept of the slack variable. Basically the slack variable says that we saw that if label into the dot product of weighted array into the characteristic array should be greater than m or equal to m. Here we would say that, let's say it like this, let it be 1 minus epsilon. I would write it clearly here. So I said that label, that is a positive and negative label, which is with me into weighted array into characteristic array, dot product of characteristic array should be greater than or equal to m into 1 minus epsilon. I simply said that I have introduced a new variable epsilon, which I will call a slack variable. So a slack variable is nothing but an epsilon which is available with me, and I said that epsilon can take any value between 0 and infinity. It can take any value between 0 and infinity, and based upon the value we can allow somewhat intermixing. So if I say that if this is the hyperplane or the classifier which I have created, so for the points which are correctly classified, I would say the epsilon is 0. When epsilon turn out to be 0, it becomes a maximum margin classifier equation, because this do not exist anymore. So we say that for the points which are well beyond the margin and are correctly classified have epsilon 0, and thus are appropriate for the maximum margin classifier, and this equation turns itself into the maximum margin classifier. But when this point has been correctly classified but the margin has not been maintained, then we say that the margin is not greater than or equal to m, but is actually less than m. What is actually less than m? So in this case we say that epsilon is somewhat, for this case epsilon is greater than 0 and less than 1. So epsilon is greater than 0 and less than 1 in this case. When this happens, then this equation turns into like this. It would somewhat be, it would be less than m. This equation would turn like this if we put epsilon somewhat, for example, if I put epsilon 0.6 between 0 and 1 for the point which appears here, this equation turns out to be less than m but greater than 0. Greater than 0 signifies that it actually exists on the right side of the plane, and less than m signifies that it actually do not maintain the margin, so it's very closer to the hyperplane. For the points which have been misclassified, we say that epsilon is greater than 1. So when epsilon goes greater than 1, then the equation turns like this. W dot y is actually less than 0. When it goes greater than 1, then this equation actually inverses its sign. When it inverses sign, it says that this point has been actually misclassified. When this has been misclassified, then epsilon goes to greater than 1. So we says that by the introduction of the slack variable in the equation, we can ensure the somewhat misclassification. Now we need some check on this misclassification. So for that we introduced a cost function. If we say the cost function is something summation of this is the slack variable. So summation of the all slack variables, all the slack variable value, and summation of them give us a cost function in a very layman terms. So if I would say there is only few misclassification, for example, in this case there is only a one misclassification, so the summation of all the uh, epsilon will come out to be small, because for every misclassification epsilon is greater than 0, and it can reaches between 0, it actually exists between 0 and infinity for every misclassification. So for every misclassification we have a higher value of epsilon, thus leading to the higher cost value. So if cost is large, means if we say that yeah, I can allow a large c value, large cost value, then this means I can allow large epsilon, a large summation of epsilon to exist, means I am allowing more and more points to get misclassified. When I'm allowing the more and more points to get misclassified, I'm actually moving to the higher bias situation, or known as underfitting situation. So the model will not give me some good or accurate values which I am looking for. In other way around, if I am say that c the cost function is very very low, in that case I am actually saying that this cost I do not encourage any large values of epsilon. So if I'm not encouraging any large value of epsilon, so I am actually discouraging the misclassification. If I am discouraging the misclassification too much, then I am saying that there should be some strict boundary between the 2 points. And when I am supporting the strict boundary, then I am moving towards the overfitting condition, where I am creating a hyperplane or classifier based upon the data available, not the pattern which is giving it to me. So I'm moving towards the overfitting situation. So we have to calibrate C such that if it gives us somewhat between the model, that is a good model which learns a pattern, not the data. I hope you enjoyed the video. Let me know if there are any questions from you in the comment section. Thanks a lot. Bye.